module in terms of the Big Data Architecture Fundamental lecture here at the JPL Caltech Virtual Summer School on Big Data Analytics. I'm Chris Mattmann. Thanks for sticking with me here to the end. So we've done a sort of hitchhiker's guide, really fast-paced history of the sort of research in software architecture, software engineering, how some of that might apply to big data. We've covered things like components and connectors, core architectural elements, styles, patterns, reference architecture. We've covered ways of capturing these sort of core elements in terms of architectural models, why you may want to visualize those. We've talked about the difference between code as implemented and what can happen when code drifts or erodes from the actual architecture and design, and what we can do to kind of deal with that, architecture recovery. And so here in the final module, I'm going to do an actual case study in the realm of grid computing to show you some of the value of software architecture and how you can actually apply it within the context of big data in your guys' applications, and then maybe wrap up with some conclusions. So this lecture actually covers a specific example that's going to bring together software architecture and big data. So you guys may be familiar, or you might not be, with the domain of grid computing. Before clouds and big data and things like that, there was grid computing. And the goal, as sort of defined by the fathers and forefathers and mothers of grid computing, was to provide an infrastructure and an architecture for basically seamlessly bringing together resources for data and compute across organizations to create virtual organizations. That was the goal of grid computing systems, circa around 2001, 2002, which was sort of the initial hot heyday, the cloud computing era, if you will, of grid computing. Okay, so we were studying those in my research group around the time. We were studying, and as we found out, there were sort of two fundamental types of grid computing systems corresponding to the two fundamental types of resources that existed at the day. There were data grids, which were really focused on federating data resources across institutions, searching them in sort of a nice and easy way. And then there were computational grids, which were focused on how do we run jobs at your institution and my institution and share sort of identities and only let these science groups do these jobs and let these other ones use these resources, and so on and so forth. So there are two predominant types of grid computing systems, data grids and computational grids from there. So we were actually writing a paper on trying to understand the architecture of grid computing, trying to mush them together, because we said, look, there were these sort of canonical papers on grid computing. There was the grid's anatomy, the anatomy of the grid, which was written by Foster and Kesselman et al. And then there was this paper called The Physiology of the Grid. The anatomy was more the architecture, the physiology was more how do we implement this thing, also written by Foster and Kesselman and Stephen Tuck and a number of people. And so we were writing a paper on our own grid technology at the time that we felt kind of consistently met this sort of requirement of sharing data or sharing compute resources and things like that. And we were writing it in the context of mobile computing. We were building this project called Glide, which was a technology it's like a mobile grid for sharing data and compute on wireless PDAs at the time, before cell phones were super popular. We submitted this paper to a workshop. We got back a review. The workshop basically said, the grid technology you're studying is nothing more than a simple object-oriented framework. And so we scratched our head and we said, was the reviewer right about this? So, I mean, a simple object-oriented framework, it really seems to fit at least the definition of grid computing in terms of these anatomy and the physiology paper, and the kind of current literature at the time. So we're wondering, is the reviewer right? How do they know that? Okay, and we were also kind of annoyed, with the review that we got. This alleged object-oriented framework was the 2003 runner-up NASA Software of the Year, okay? So we basically started to do a little bit more research and look around at the time, which you guys might do here, maybe as PhD students or postdocs or as practitioners in the realm of big data. And we started to look at the research literature in terms of architectures and grid computing. And we basically found out that and still kind of persists to this day, that little was sort of known in terms of the architecture of the as-implemented grid computing technologies of the day. There was a study by Finkelstein et al. That was published in the Journal of Grid Computing, in which they were trying to look at things like requirements and so forth, but they didn't really know much about the architecture of it, the components, the connectors, the stuff that we're talking about here in the summer school, okay? Little was known about that. And so, there's this big risk if you, know a little bit about the requirements, but you're not exactly sure of how that maps, and how that went through the design process and how that went through the architectural process to the eventual implementation. It's a big risk of architectural drift or erosion, as we were just talking about, in the second module of this course. right? It seems like grid technologies all generally claim to have the same capabilities, but they seem to be implemented in vastly different ways, have different sort of requirements that they're satisfying, and so on and so forth. Maybe evidenced by the reviewer that was reviewing our paper at the time. So we developed an approach that's based on what you're learning here in terms of software architecture and related to big data and so forth, because grid computing is arguably within that realm. We developed an approach to studying initially 5 and eventually almost 20 grid computing technologies and their implementations. And we developed an architectural approach to studying these technologies, and I'll talk about it. So we had to select software codes. We decided to select grid computing technologies that were object-oriented, simply because some of the techniques we used to recover the architecture were real amenable to that. We wanted them to be open source because we want to be able to look at the source code being the most, like I said, up-to-date version of the software and most sort of canonical representation of your system sort of as it evolves. And we also wanted to use kind of off-the-shelf systems that seem to have a big user base. So these were the initial 5 that we studied. We studied Globus, which was the de facto grid technology at the time, ODT, DSpace, Glide, our own technology, because we wanted to put it to the test. We were building, and something called JC Grid. And that was where the initial 5 technologies that we studied in 2005, 2006, having since expanded the study to include over, like I said, 20 grid technologies circa 2009, 2010, including Hadoop, things like Wings, Pegasus, and so on and so forth, some more modern technologies. So our approach was to initially do sort of a detailed literature review and to try and look at the 4 seminal grid papers at the time, which was this data grid paper by Anne Shervenak, as well as 3 papers from Foster and Kesselman on the grid's anatomy, its physiology, and a checklist of what it means to be a grid software technology. So looking at these literatures allowed us to distill a set of reference requirements. Where have you guys heard that before, right? We talked about reference architectures and domain-specific software architectures. We came up with a set of reference architectures for reference requirements for the domain of grid computing. And so for each requirement we derived from studying the literature, we also defined a layer in the classic 5-layer grid architecture, which I'll talk about here in the next slide. We mapped the requirement to which layer it actually had to do with. So if the requirement had to do with sharing resources across multiple organizations, it likely went in the collective layer, which is responsible for that. If it had to do with application or building sort of applications on top of the grid computing infrastructure, we mapped that requirement to the application layer, and so on and so forth. And then what we did is for each of the technologies, initially 5, eventually 20, like I said, we applied one of these sort of more automated clustering, static analysis, dynamic behavior, architecture recovery techniques. We actually applied one called Focus, which was developed by Medvedevich and Jakubak, to these open source code bases to arrive at sort of a partial architecture recovered model. And we used these reference requirements as well as the layers that they map to help us guide and shoehorn which one of the layers, the components that we recovered and the connectors in this partial recovered model actually went into. Okay, and then we studied that. So the approach is sort of depicted graphically here. There's a 5-layer grid architecture. Real quickly, the layers correspond to fabric. These are like the data disks, the storage devices, the actual physical processors and things like that across a grid. A connectivity is all the networking layer and things like that that make these available via network devices and make these resources available in a networked way. Resources are specific individual resources, services in a grid environment specific to a single institution. Collective is a layer on top, and by the way, you're seeing this in the upper left-hand corner of this diagram, which is sort of the 5-layer grid architecture as defined in these papers. Collective is multiple resource sort of services across multiple potential institutions. It's what allows sort of this virtual organization to deal with resources across multiple institutions, find them, find compute, find storage, and so on and so forth. And then application or applications that are grid enabled that are built on top of this sort of underlying infrastructure and then interact with them. So that architecture was found in the physiology and the anatomy paper. We studied that. We pulled that right out of there. That's in the upper left. The reference requirements were distilled by studying those papers and the data grid paper, amongst others, these sort of 4 seminal papers. And then for each grid technology source code there on the right, we took the source code, any documentation, anything else we found, and we ran it through this sort of focus process to produce this initial sort of recovered architectural model. We then compared those reference requirements to see if it could give us any more information about the components and the connectors, and we shoehorned those into the upper left there, into those the actual sort of prescribed grid architecture to see how well the implementations of these grid technologies conform to what they said the grid architecture should be. And we use this as sort of a metric to determine, like, okay, how well does our technology do? Because remember, the original impetus for this was someone told us our technology wasn't a grid technology. It wasn't a grid software system. So we wanted to develop sort of a tried-and-true research approach, a scientific approach for verifying this. Okay, so I basically talked sort of through this visually on the last diagram. Again, we clustered our components according to sort of the reference architecture and shoehorned them in there from that recovered architectural model, which we sort of gleaned according to that focus approach that we had, and then we used the reference requirements to sort of give us further information about what layer in the grid architecture the components or the connectors should sort of go into. And so these are the reference requirements, the list of around 17 that we gleaned from that basic grid literature, and the sort of impacted layer in that grid architecture that sort of gave us some more insight as to, well, you know, if it's something that's dealing with single sign-on, it likely goes in the connectivity layer, and so on and so forth. So this is a sort of sequence of steps that we took. We did these sequence of steps for all of the grid technologies that we were looking at. This happens to be, in the upper left, a static class diagram of the Apache ODT software, object-oriented data technology. And starting from the upper left and following A, B, C, going down that column on the left, and then up again to D on the right, down all the way to F there at the bottom, that's sort of the steps of focus. Focus is a clustering technique. It's a graph sort of clustering technique that sort of looks at coupling and cohesion, the relationships between these sort of classes. Remember, they're object-oriented codes, so we're talking about classes and relationships between classes like generalization, inheritance, and things like that. So focus is a graph clustering technique that allows us to sort of measure the coupling and cohesion between these to try and derive what classes are related and to suggest they might be a component, what classes are interacting with one another to suggest they might be a connector, and so on and so forth. So we ran sort of ODT and all the other technologies up to 20 eventually, like I said, through this process. We ran them through Mr. Wizard here, and what we get out the other end is this sort of recovered architectural model, when none of the clustering techniques for focus, when it sort of synthesizes, when it sort of arrives at a point where they can't really be clustered anymore. That's basically this recovered architectural model. It's a partial recovered architectural model. It doesn't have all of the detail, the styles, the configurations, and all that, but it has some basic information about components and connectors and things that we can work with, and which we did work with according to the process that we talked about before. We took this recovered architectural model, and then we shoehorned it into the grid reference architecture, those 5 layers. Okay, again, with those reference requirements that gave us some insight, which we distilled from the literature to figure out which layer it went into, as well as just with looking at things like documentation and any other information that we could find. And what you find is that, you know, does this sort of look perfect? Well, let's see. The canonical layered architectural style has the following constraints. First, any layer in the layered architectural style should only be communicating with its adjacent most layer. Communication should flow top to bottom, looking at this in a vertical way, the topmost components being sort of client-consuming components, or layers, if you will, and the bottommost layers or components being service-providing layers to all of the above sort of layers and components above it. Okay, so things on the bottom should be service providers to things on the top and layers on the top, right? And again, any 2 layers, communication should only happen between any 2 layers, not from, for example, the top layer all the way down to the bottom layer. Okay, so do you see anything wrong with this picture? It might be hard to see unless you sort of look at this, so let me help you here. There are all sorts of things that are wrong, all sorts of violations. You see components here in the application layer crossing a 2-layer boundary to get down to the connectivity layer, okay? You see upcalls. You see components in the actual fabric layer making an upcall to a component in the resource layer. Okay? You see things like components that we couldn't determine the right layer that it went into. All right? We just didn't have enough information, or we couldn't tell. What about this one? This is Globus's recovered architectural model. Okay? Whoa, 2-layer boundary and upcall. All 3 of them right there. What else? 5 components that we couldn't determine which went in the right layer. And Globus is a comparatively larger system, than OODT, but it still exhibits the same, if not more, sort of basic characteristics for that. And we found this in a number of the software systems that we were looking at. Up call, right here. So basically, there were numerous violations of the reference architecture. There were things like component up calls, which indicates sort of definitely a violation of the layered architectural style, but potentially indicates architectural drift or erosion. Components or code, in the actual code, that originally weren't designed to talk to one another, but that are talking to one another there. Crossing 2 or more layer boundaries. This typically indicates developer sloppiness. You had a library that you intended for other sort of elements to sort of call, or the most adjacent elements to that to have some sort of coupling to it, but you find later on down the road shoehorning and bolting on components that you just decided to make call this library even though they're nowhere related in the software system at all, or nowhere related in the actual architecture as well, right? And then there were just, it could be a refactorization problem, it could be a number of things. But, and then there are some components that you just, at the end of the day, you look at your code and you're why is this here? It's not being called by anything. Nothing, it doesn't really have a purpose. So, look at all the types of information that we could glean from performing this type of process. Okay, what we gleaned from that is that, grid technologies tend to be sort of a domain-specific software architecture for the realm of grid computing, right? They exhibit a core set of reference requirements. They have a sort of kind of similar components and styles, even though there are violations. They have a large variation in terms of their size and number of components and cardinality and things like that. They also have optional requirements, right? And this are identified through, not all grids satisfy these sort of collective level requirements. Not all of them satisfy even these layer-specific requirements for that, okay? So, it seems like single sign-on is optional. It seems like, data grids are optional, okay? And also a distinction between data grids and computational grids, right? In terms of the identified requirements for that. Okay, so these were sort of the results of our study, just taking sort of an analysis of, the actual code and its mapping to software architecture. And these actually led us to develop and publish, basically we're working with the Journal of Grid Computing, to publish a new architecture for grid computing that actually more carefully and accurately represents the architecture based on all of these purported grid technology, these grid codes, and so on and so forth. And this was simply by looking at the architectural styles, the components, and things like that as derived from the code, and needing things like architectural recovery and processes like we've talked about here. So applying and figuring out how to think through and how to sort of discern the differences between these large-scale software systems, and you have this in big data too, identifying which requirements are optional is really important. They may tell you when you build your next system, you don't need to include components or software that supports that and save you money, time, resources, and a number of other things. Okay, so just thinking about and having this sort of basic understanding of software architecture, components, connectors, the basic elements, styles and patterns, how they apply, what they suggest, what should be true, what shouldn't be true about them, has a real big impact on software systems, okay, and your big data systems. There's a lot of related work. I'm not going to go over this. I leave it here for you guys to sort of peruse. The idea is, grid systems, software systems typically have a hard time following the architectural style, and that's just because there's a lot of overlap between grid layers, and software systems in general are hard to understand unless from an architectural perspective, especially when they get large. You're dealing with big data systems, frameworks, middlewares, libraries. The only way to truly properly understand them is to approach them from the realm of software architecture, right, which is a summarization, if you will, of the principal design decisions about your software system. There's lots of work kind of going on and areas for people to expand this. I encourage you guys to take a look. I encourage you to take a look at some of these pointers, again, to my software architecture class at USC, to my homepage, and then all of the data behind this particular study of grid middlewares is available on the following 2 links and websites, including the data for the submitted paper to Journal of Grid Computing. So I encourage you to take a look at that too. I encourage you to contact me if you have any questions. I'm Chris Mattmann, and thank you. This ends the first full module here on big data architecture fundamentals. Thanks.